Imagine a heavy freight cart moving smoothly along a track. No friction, no resistance, just pure motion. Let's imagine we have a 6,000 kilogram freight cart moving at a constant speed of 12 meters per second. Above the track, there's a platform holding a 2,000 kilogram crate completely at rest. Suddenly, the crate is dropped into the cart. The crate stays inside, and both move together afterward. So the big question is, what is their common speed immediately after the crate lands inside of the cart? To solve this, we have to use the law of conservation of momentum. Because the track is frictionless, there is no external forces acting upon the system. That means the total momentum before the collision is equal to the total momentum after the collision. So before the collision, the cart is still moving and the crate is still at rest. So the initial momentum comes only from the cart. Alright, let's make sure to dot all our I's and cross all our T's. So make sure, let's go over our given values. We have the mass of the freight cart, which is 6,000 kilograms. The initial velocity of said freight cart would be around 12 meters per second. The mass of the crate, which is 2,000 kilograms, and the initial velocity of the crate is 0 meters per second. So, after the collision, the crate stays inside the cart, so both objects move together with a common velocity, v. Step 1, let's guarantee our logic here. Since the track is frictionless, there are no external horizontal forces acting on the system, except of course the vertical force, which is gravity. Therefore, the law of conservation of momentum applies to our problem. Thus, we can equate our total momentum before the collision equal to the total momentum after the collision. So step 2, let's write the general momentum equation. Momentum is defined as P is equals to mv. So for a problem which has two objects, we would have this equation. For us to derive this, we can see here that there are two v values. Thus, we can transpose or transform the equation into this much simpler form. This is the derived working equation for a perfectly inelastic collision. Step 3, we simply substitute our known values. So we have this equation. And lastly, step 4, we simply solve for our final velocity. We have here v, which has now already been isolated onto one side. We have v is equals to 72,000 divided by 8,000. And now we have our final answer, which is 9 meters per second. Thus, our final answer is that the freight cart and the crate, after collision, move together at 9 meters per second. That's the answer.
Imagine you're floating in the silent, endless darkness of outer space. No friction, no air resistance, just you, your spacesuit, and a small tool in your hand. Now, what happens if you throw that tool forward? Today, we're going to explore exactly that. Now, here's the problem. An astronaut with a spacesuit has a total mass of 90 kilograms and is at rest in space, holding a 5 kilogram tool. The astronaut throws the tool horizontally forward at a speed of 8 meters per second relative to space. What is the recoil speed and direction of the astronaut after throwing the tool?
To understand what happens, we need to understand a rule of nature that becomes especially powerful in space: the law of conservation of momentum. Momentum is basically the substance of a moving object. Mathematically, it's written as momentum is equal to mass times velocity. But here's the important part. If no outside forces act on a system, like friction, wind, gravity, or a solid wall, the total momentum must stay the same. And in space, when you're floating freely, there are no outside forces acting on you. This makes you and the tool a closed system. Before anything happens, let's look at the system. The astronaut plus the tool have no motion, no velocity, and no momentum. So the total initial momentum of both the astronaut and the tool is 0. When the astronaut throws the tool forward, the tool now has momentum because it's moving. But the universe demands balance. So if the tool gains forward momentum, the astronaut must gain an equal and opposite momentum. This is a representation of Newton's third law in action, the law of interaction, which states that for every action there is an equal and opposite reaction. So now let's translate this into equations. So for the problem, we're given the mass of the astronaut and the suit together is 90 kilograms. The mass of the tool is 5 kilograms. The velocity of the tool after the throw is 8 meters per second forward. The velocity of the astronaut after the throw is unknown. By the law of conservation of momentum, momentum before must equal momentum after. Since the momentum before was 0, we write 0 is equal to 5 kilograms times 8 meters per second plus 90 kilograms multiplied by velocity. What we're saying is that the tool's forward momentum plus the astronaut's backward momentum must always add up to 0. Now, let's solve the equation step by step. So we will have the equation 40 kilograms meters per second plus 90 kilograms multiplied by velocity is equal to 0. Well, how did we get 40? 40 is the result of the momentum of the tool, wherein we multiplied 5 kilograms by its velocity of 8 meters per second. Now, in order to isolate VA, we must move 40 and divide it by 90 on the other side of the equation. So our resulting equation is VA is equal to negative 40 kilograms meters per second divided by 90 kilograms. And we will have a resultant velocity of approximately negative 0.44 meters per second. This problem is a beautiful example of the combination of the definition of momentum, conservation of momentum, Newton's third law, and the physics of free space, all working together to show that even the smallest action in space has a noticeable reaction.